Assalamualaikum and good morning. We are Group CS248682 and today we are going to present our graph theory project entitled Optimization of Municipal Waste Collection Network in Seremban using Minimum Spanning Tree Algorithm. This project focuses on applying graph theory and classical minimum spanning tree algorithm to optimize the municipal waste collection network in Seremban by identifying the minimum road network that connects all selected waste collection locations efficiently. Before we begin, we would like to introduce our team members as shown on the screen. Now I will start with the introduction of our project.
First, I would like to explain the background of this study. Graph theory is a branch of mathematics that is used to model and analyze networks. It represents location as vertices, connections, and as edges, and assigns weights such as distance or cost to each edge. This allows optimization techniques to identify the most efficient network structure. In this study, we apply graph theory and Kruskal's minimum spanning tree algorithm to optimize the municipal waste collection network in Seremban by finding the minimum road network that connects all selected locations efficiently. Now, let's look at the problem addressed in this study. SWM environment is responsible for collecting municipal waste from multiple locations across Seremban. As the number of waste collection points increases, the road network becomes more complex. If the network is not optimized, waste collection vehicles will travel longer distances, consume more fuel, incur high operational costs, and produce greater carbon dioxide emissions. Therefore, an efficient road network is needed to improve the waste collection process and support sustainable waste management. To solve this problem, we model the municipal waste collection network using graph theory. Each waste collection location is represented as a vertex, while the roads connecting the location are represented as edges. The driving distances obtained from Google Maps are used as the edge weights. Finally, Kruskal's minimum spanning tree algorithm is applied to determine the minimum road network that connects all selected locations with the shortest total travelling distance. Next, I will explain the problem modeling. The municipal waste collection network is modeled as a weighted undirected graph. The selected locations are represented as vertices, the roads as edges, and the driving distance as edge weights. This model is then analyzed using Kruskal minimum spanning tree algorithm to determine the most efficient road network. Now, these figures shows the study area in Seremban, Negeri Sembilan. The network consists of the SWM Environment Operational Depot and 6 major waste collection locations, which consists of Terminal 1 Seremban, Seremban Gateway, Tuanku Jaafar Hospital, Maidin Seremban 2, Taman Rasa Jaya, and SMK King George V. The driving distances between these locations were obtained from Google Maps and used as the edge weights. Now, this table shows the 7 vertices used in the network. Vertex A represents the SWM Environment Operational Depot, while vertices B to G represent the selected waste collection locations. Together, these vertices form the municipal waste collection network analyzed in this study. Next, each edge represents a direct road connection between two locations, while the edge weight represents the driving distance in kilometers obtained from Google Maps. Since waste collection vehicles can travel in both directions, the network is represented as a weighted undirected graph. These edge weights are used as the input for Kruskal's algorithm. Finally, this figure illustrates the weighted graph of the municipal waste collection network. The vertices represent the selected locations, while the edges represent the road connections with each edge labeled by its driving distance. This graph serves as the mathematical model for applying Kruskal's minimum spanning tree algorithm to determine the minimum road network connecting all selected locations.
The municipal waste collection network was optimized using Kruskal algorithm, a greedy algorithm to find the minimum spanning tree (MST) of a connected weight graph. The algorithm works by selecting the route with the shortest distance while ensuring that no cycle is formed. The process continues until all 7 locations are connected using 6 edges, producing the minimum road network. First, all edges were sorted in ascending orders. Kruskal algorithm then selected the shortest edges one by one. Edges that form a cycle were rejected, while the other were accepted. After 6 edges were selected, all 7 locations were connected, giving a total travelling distance of 19.9 kilometers. In this figure shows the minimum spanning tree obtained after applying Kruskal algorithm to the municipal waste collection network. The final network consists of 6 selected edges which successfully connect all 7 waste collection locations without forming any cycles. Since a graph with 7 vertices requires 6 edges to form a minimum spanning tree, the result satisfied the MST condition. Compared with the original network, The optimized network reduced the number of road connections from 21 to 6 and decreased the total traveling distance from 119.1 kilometers to 19.9 kilometers. This shorter network is expected to reduce fuel consumption and operating costs while maintaining the connectivity among all waste collection locations.
Now, we will walk through our Python implementation step by step to show how we model our waste collection network and solve this using software. Starting with step 1, we import our two main working tools, NetworkX, which we use to construct the graph map and run our sorting algorithm, and Matplotlib, which help us draw the network maps. In step 2, we create a function called createWasteNetwork. Here, we build an empty graph G and set up our 7 locations as node from A to G. We also define an array called node colors, where we give each specific neighborhood its own color code so they are easy to tell apart on the final map. In step 3, we type in our edges with distance list. This holds all 21 real-world driving routes and their exact kilometer weight that we took from our dataset map. We use g@weight_edges prompt to fit all these routes into our Python graph model. In step 4, we start building our plotting function to stop the lines from crowding each other and blocking out the numbers in the center of the screen. We tell Python to use an circular layout. This automatically pulls all the neighborhood letters outward into a clean, perfect circle. Next, in step 5, we program the specific visual settings for our graph plots. We set the node size and bold level and use edge levels to overlay the kilometer distance numbers directly on top of the connection lines. And in step 6, we write our main execution block. The code automatically calculates the initial distance matrix for our messy unoptimized map. We use the vital line and X maximum spanning tree, specifying the algorithm cross-curl. This triggers the computer to automatically select the shortest routes while instantly breaking only any overlapping loops. In step 7, the code sets up our final text summary printout. It sorts the chosen optimal routes from the shortest distance to the longest. It also prints out our final calculated optimization matrix. Finally, in step 8, the 7 triggers the plot graph function to display our multicolored circular network maps on the screen. This concludes the step-by-step walkthrough of our software implementation. Here's our output calculated by our Python program. At the top, we can see that our original network setup had 21 available routes, creating a very long total driving distance of 121.10 km. In the middle, the program lists the 6 best routes chosen by classical algorithm, automatically sorted from the shortest distance to the longest, starting from route B to G at 1.9 km up to route A to F at 5.1 km. At the bottom, we can see our final success matrix. Our new optimized tree layout uses just 6 strategic routes instead of 21, cutting our total distance down to only 1990 km. By removing all the useless overlapping loops, we achieve a total operational distance save of 101.20 km. These massive drops prove our new layout will drastically lower fuel costs and greenhouse gas emissions for the town.
Next, I will discuss the finding of the study. The results show that Kruskal's algorithm is an effective method for optimizing the municipal waste collection network in Seremban. By selecting the shortest road connection without creating cycles, the algorithm will successfully generate a minimum spanning tree or MST consisting of 6 roads connecting with a total traveling distance of 90.9 kilometers. When compared to the original network, which contained 21 road connections with a total distance of 119.1 km, the optimized network significantly reduced unnecessary road connection while still maintaining full connectivity among all selected waste collection locations. This demonstrates that the MST provides a simpler and more efficient network structure. Although the study focused on minimizing traveling distance, the shorter route has the potential to reduce fuel consumption, operating costs, and carbon dioxide emission. Therefore, the proposed network could contribute to a more efficient, sustainable municipal waste collection system. In addition, the manual calculation and the Python implementation produce the same minimum spanning tree and total traveling distance. This confirms the accuracy and reliability of the optimization process. However, the study has several limitations. Factors such as traffic condition, vehicle capacity, and waste collection schedule and road condition were not included in the model. Therefore, future studies could incorporate these factors to develop a more practical and comprehensive waste collection optimization system. Lastly, I will conclude the study. This project successfully applied graph theory and Kruskal's algorithm to optimize the municipal waste collection network in Seremban. The waste collection location will represent as vertices, while the connecting road will represent as weighted edges based on their traveling distance. By applying Kruskal's algorithm, the minimum spanning tree was obtained, consisting of only 6 road connections with a total traveling distance of 19.9 kilometers. Both the manual calculation and the Python implementation produce the same result, confirming the correctness and reliability of the optimization process. Compared with original network, the optimized network reduces unnecessary road connection while maintaining full connectivity between all waste collection locations. Although this study only considered traveling distance, the shorter network has overall. The proposed graph model provides a useful reference for planning municipal waste collection networks and demonstrate the practical application of graph theory in solving real-world optimization problems. For future work, the model can be further improved by incorporating real-time traffic condition, travel time analysis, vehicle capacity constraint, and varying waste collection demands to produce a more practical and comprehensive waste collection optimization system.